this statement here that we need to prove by mathematical induction then. So here, the first step is we have to show that this is true for n equals to 1 here. So step number 1, we need to show that. So we need to show that this is true when n, or for n equal to 1 there. So we get this expression here, we equate it to the right hand side, then where there's n there we substitute with 1. So we have 3 to the power n is equals to 3, open brackets, 3 to the power n minus 1, we close the bracket there, then we divide by 2 here. So where there's n here we substitute with a 1, so we have 3 the power 1 here is equals to 3, open brackets, 3 to the power 1 minus 1 divided by 2 here. So this will give us 3 is equal to 3, open brackets, 2, we close the bracket there, divided by 2. So this will give us 3 times 2 will give us a 6 here, divided by 2 it will give us a 3. So here we have that our 3 here is equal to 3 there. So meaning that we've proved to say it is true for the first term, which is when n is equals to 1 here. So therefore we say therefore true for n equals to 1. Okay, so we go to the next step now. Let me just scroll down a bit. So the next step is the inductive hypothesis. So on the inductive hypothesis, we make an assumption that the statement is true when n is equals to k. So here we go to the inductive hypothesis. So on the inductive hypothesis here, we make a claim, or we assume to say that it is true for n equals to k there. So we assume that it's true when n is equals to k here. So what we just do here is we get our expression the way it is, then where there's n there we just substitute with k there. So we have 3 plus 9 plus 27 plus 3 now to the power k. So we substituted where there's n there, we put k equal to 3, open brackets, 3 to the power k minus 1 divided by 2, like this here. So on the inductive hypothesis, this is the only thing that we get to do here. So now we need to back our inductive hypothesis here by saying we show that it is also true when n is equals to k plus 1. So meaning that we add a new term to the terms that we have already this side here. So we're saying we show that it's also true when n is equals to k plus 1 here. So this side we have our 3 plus 9 plus 27 plus 3k, or 3 to the power k rather, plus 3 to the power k plus 1. So this is the ak plus 1 term that we're adding here to the sequence that we have already this side, or to the terms that we have already. So this will be equal to now 3, open brackets, 3 to the power k plus 1 minus 1, like this here. And everything you divide by 2. So on the left hand side here, if you look at the terms starting from the first term here up to the k term that we have here. So we have from this term up to this term here. You'll notice to say that this gives you the expression that we have on the inductive hypothesis here. So we get the right hand side on of the expression that we have on the inductive hypothesis, and we make a substitution there. So we have 3 open brackets 3 to the power k minus 1 divided by 2 plus 3 to the power k plus 1 is equal to 3 open brackets 3 to the power k plus 1 minus 1, then we divide this side by 2 here. So now our main target here, or goal rather, is to show that the left hand side that we have there is equal to the right hand side here. So let's go ahead and simplify the expression that we have. So here this here will give us 3 to the power k plus 1 minus 3. So we have 3 to the power k plus 1 minus 3 here divided by 2, and this side plus 3 to the power k plus 1 this side. It's equal to 3 open brackets 3 to the power k plus 1 minus 1 divided by 2 here. So now here, if we make these two here a single fraction, these two fractions that we have here a single fraction, we're going to have 3 to the power k plus 1 minus 3 plus 2 multiplied by 3 to the power k plus 1, then everything here we divide by 2 is being equated to 3 open brackets 3 to the power k plus 1 minus 1 divided by 2 this side here. So now these two terms that we have here, this term that we have here and this term that we have there, this is 3 to the power k plus 1 and this is 3 to the power k plus 1. So 3 to the power k plus 1 here, we treat it like a variable the same way we treat x plus x or 2x plus 1 or 2x plus x rather. So it's the same thing that we do here. So here it means that we just add the coefficients of 3 to the power k plus 1 and this side 3 to the power k plus 1. So notice to say that when we do that, we're going to have 3 to the power k plus 1 minus 3 divided by 2 there. This is equal to 3 open brackets 3 to the power k plus 1 minus 1 divided by 2 here. So once we do that, we can just factor out a 3 this side. So if you factor out a 3, you have 3 to the power k plus 1 minus 1 divided by 2. This is being equated to 3 to the power k plus 1 minus 1 like this. Everything divided by 2 here. So we've shown to say that the left hand side is equal to the right hand side. So now if this is the case here, then we can just conclude to say, therefore this is true for n equals to k plus 1. So if this is true for n equals to k plus 1, then this holds under mathematical induction for every natural number n here. So just say this holds under mathematical induction for every natural number n. Okay, let's look at the next question again.